Welcome to this video describing the y86 architecture. The y86 is a teaching architecture based loosely on the x86, albeit much simpler. By the end of this video, I hope that you too could explain the y86 to someone else. You can explain how the move instructions work, how addressing works, and trust me, it's way simpler than the x86, and also how to read and write simple y86 programs. You may have seen this image before in a course or maybe even in the textbook. And I call this the artist's rendition of a CPU because it greatly oversimplifies what modern processors look like. We will in fact present the y86 as if this is what a processor looked like. But in reality, processors are greatly more complicated. This is actually what a modern processor looks like. Here is an overview of the y86 processor. This is all the state that is visible from the assembly language. Another way of saying that is that this is what the instruction set architecture, or ISA, references when it talks about the y86 processor. In reality, the implementation can be dramatically more complex. Let's begin with the register file. The y86 has 15 registers. You'll see that the names are quite similar to those you might have experienced with the x86, and then it has some other ones. You'll also notice that R15 is suspiciously absent. The reason for that is because that is going to refer to an invalid register. Registers are where we typically do a lot of the computation because they're implemented with very high-speed memory, in contrast to main memory, or DRAM, which by comparison is relatively slow. The next part of the visible architecture are the condition codes. The y86 has 3 condition codes: a 0 flag, a sign flag, and an overflow flag. These condition codes are set on arithmetic or logical operations, and you'll see that we can use those to do conditional instructions like jumps and moves. Next, we have a status register that tells you what's going on with the processor. Normally, you'll see it in state 1, meaning that everything's fine. When the processor is halted, it'll move into state 2, and if you encounter some bad addresses, you might find yourself in states 3 or 4. Next, we have the program counter, which tells you what the next instruction is that you're going to execute. And finally, we have main memory, referred to as DMEM in the book, and you can think of this as the DRAM in your actual computer. I'm going to present the y86 instructions as a set of classes. So today, we're going to start with very simple instructions of halt and no op, and then look at the move instructions, and in fact, only a limited part of one of the move instructions. Then, in later videos, we'll look at stack operations, arithmetic logical operations called ALU operations, the jump instructions, and then function call and return. For now, what I want you to take away is that there are 4 basic formats for instructions. You can have 1-byte instructions that are simply an opcode with an optional function. You can have 2-byte instructions that take what you have in 1-byte instructions and add the possibility to assign 2 registers to the instruction. The 9-byte instructions include an opcode, a function, as well as a destination address. And then you can put everything together and have an instruction that has an opcode and function, registers, and a 64-bit value. And as we go through the different classes of instructions, you'll see how each of them manifest in one of these encodings. Let's start with the really simple ones. So 00, i.e. opcode 0 and no function, is a halt. And what that does is exactly what you think: it stops the processor. A similarly simple instruction is the no op, which has opcode 1 and function 0. Let's start with the simplest move instruction, which is moving data between 2 registers. To move data between 2 registers, we're going to need one of these 2-byte instructions because we'll need the opcode and the function, as well as an indication of the 2 registers that we're accessing. So the opcode for a move RR is 2. For now, we're going to put 0 in the function. We're going to come back to that a little while later. And then we're going to indicate the 2 registers that we'll manipulate as RA and RB. So when we say RR move Q, %R8, %R9, there's a bunch of things loaded into that.
First of all, the two R's at the beginning tell us that we're moving register to register. And you'll see in other instructions that we'll change those values to move, for example, immediates into registers. The last letter, the Q, says that we're moving a quad word, which is 8 bytes. Now, R8 and R9, this says we're going to move what's in register 8, the value in R8, into R9. The way we describe that, using the notation from the book, is shown right under the register file. We say the register file, the location indicated by RB, which is R9 here, the destination, is going to get filled with the value that we get by looking in the register file at index RA. So this says take what's in RA, the value in the RA register, and put it into the RB register. We encode that in the instruction with the 2 for the opcode, and then by placing the values 8 and 9 in the 2 register fields. The beauty of this representation is that you can then read out those nibbles. Half a byte is a nibble, so you can read those out and you get exactly what the representation in memory will look like in hexadecimal. Next, let's look at how we move a value into a register. So we call values immediates, i.e. the value is immediately there. So in this case, the instruction is going to be IR, move from immediate into register, move Q, we're still moving a quad word. So this time, in addition to the opcode, this time it's a 3, and the registers, this time we have a destination register, RB, but we don't have a source register, so we use F, which is our unused register. We're also going to need the immediate value, which is the value we want to put in the register. And this is going to be an 8-byte quad word value. So in this case, we're taking the constant cafe and moving it into R9. So you see that we have R9 where RB is, but you'll notice that the ordering of bytes for cafe is not necessarily what you expected. And the reason is that the y86, like the x86, uses a little endian ordering. And what little endian means is that you put the least significant byte first. So when you look at cafe, FE are the least significant values, so those go in the first byte, then CA. So as you read out the value, you'll see that the instruction encoding is pretty easy to read, but the byte ordering is going to look a little bit funny as you read it out of memory. And within a few days, you will become completely comfortable translating that kind of representation. Next, let's look at the instructions for moving data to and from memory. We'll start with taking a value that's in memory and moving it into a register. Unsurprisingly, the instruction for that is the MR, move Q. In order to understand these instructions, we're going to have to understand the addressing modes that the y86 supports, or I should say addressing mode, unless you consider immediate a mode. So when we want to refer to a memory address, the way we're going to do it is we're always going to refer to it by an offset plus the contents of a register. In this example, let's assume that the stack pointer is pointing to the address 0x4000, and the value that we want to move from memory into the register resides at the address 4000 plus 4. The way we represent that is that we refer to the register RSP in parentheses, and then we put the offset before that. So if you look at the instruction here, what that says is take the value located at 4 bytes off of the stack pointer, which means you take the contents of the stack pointer, in this case hex 4000, you add 4 to it, and that gives you the address in memory where we're going to get the data. And then what we're saying is now move that data into register R9. The opcode for this instruction is a 5. So once again, we have 5 with no function or 0. Now we do need 2 registers here, and you're going to find that we're no longer going to put R9 as the destination register. And the reason is that when we do address computation, we're always going to do it on the RB register. So in this example, because we're doing address computation on the stack pointer, which is register 4, we're going to put 4 in that RB field, and therefore the register into which we're putting the data is actually going to occupy the R9 field. So as you look at the encoding, we see 50 for the opcode and function, but then we see 94, R9 is the A register, and 4, the stack pointer, is the B register. Once again, like we saw in the immediate instruction, we're going to encode the offset in little endian. So 4 is the least significant byte, and so that goes first, and all the other bytes are zeros. So what we're doing here is we're taking the contents of RB, we're adding that to the value, or this address offset D that appears in the instruction, and then we're using that as an index into memory and saying take the 8 bytes that start at that address and move those into the register represented by RA. Unsurprisingly, the instruction that goes in the opposite direction looks very similar. So what happens when we want to move from a register into memory, otherwise known as a store? We'll use the same syntax for addressing mode, and we'll use the same register. And this time, it actually makes a little bit more sense because RA is in fact the source here, R9. We're taking something out of the R9 register and we're putting it in memory. And we're going to describe the memory location just like we did before. So in this example, we're saying take the value in R9 and move it into the memory location represented by 4 plus the stack pointer. Let's wrap up by looking at a simple example. In this case, we're going to write a program to swap two values. On the left side, we're going to do it all in registers. So we'll begin by initializing the registers RAX and RBX to contain two values, face and cafe. And our goal is that by the end of this, RAX contains cafe and RBX contains face. As you know, very often when you want to write a swap routine, you need a spare variable. So in this case, we'll use register RCX. So we'll use the register to register moves to take what's in RAX and put it in RCX to save it. Then we can overwrite RAX, so we move what's in RBX into RAX. And then finally, we take our saved value in RCX and put it into RAX. That was all pretty straightforward. Let's try to do the same thing, but this time, let's assume the data is in memory, and in fact, we want to swap it in memory. So on the right-hand side, that's what we're going to do. And you'll notice something new at the bottom. In addition to the assembly language, we have things which are called assembly directives. Things in your assembly program that begin with dots are notes to the assembler. So in this case, it says, the dot pause says, at this point, pretend you're at address 100, and the next things I put here, put them at address 100 in this program. And in particular, what I'd like you to put here are two variables. The first one I'm going to call A, so I'm using a label. The colon says here's a label, and it is the next address. And I'd like you to allocate a quad word, or 8 bytes, and into that 8 bytes, I'd like you to store the value face. Similarly, I'm going to call the next location B. It's also a quad word, and it's going to contain the value cafe. So this is how we declare data in our programs. And our goal is that after we execute this program, the memory location A contains cafe and B contains face. The way I'll do that is I'm going to take the value of address A and put that in R11. So in the other example, I showed you actually specifying a hex value. In this example, you can also specify a label, and it will take the address of that label and put it into the register. So now R11 you can think of as a pointer to A. And now what we want to do is we're going to read the values out of memory. So at a 0 offset from R11, i.e. value A, we're going to put that in RAX. And then 8 bytes later, which would be the location of B, we're going to take that value and put it into RBX. Now, instead of using a temporary location, those two registers, RAX and RBX, are temporary locations. So I'm going to now store the values they contain directly back to memory. But this time, I'll take what's in RAX and I want to put it in location B, so that's 8 added to R11. And what's in register RAX, what's in register RBX, I'm going to put in location A, which is 0 bytes offset from R11. Simulator. If you go to the Canvas site and click on Simulator, that will take you to a simulator that is, voila, a y86. I have conveniently set up a file, which I'm going to load. The register one you can run on your own. Let's run the one where we use memory. So here's that second swap program. So what we can do is we can actually run the simulator one cycle at a time and watch what happens. Before we start, notice that cafe and face are here in memory at address 100, just like we told them to. So when I run one cycle, the first thing I'm doing is I'm taking A, i.e. the address where that A variable is, and I'm putting that in R11, and sure enough, R11 now contains the value 100, which is where I told the assembler I wanted to place these data variables. Next, I'm going to do my 2 memory register moves by taking what's at 0 off of R11, or A, and putting it in RAX, and 8 off of R11 and putting it in RBX. So ideally, RAX now contains face, and one more cycle, RBX now contains cafe. Great. Now what I'm going to do is take those values and put them back into the opposite locations. So the next instruction should take what's in RAX, i.e. face, and it should change memory. So let's see what happens. And voila, now look, both of the memory locations contain the same thing. But now what I'll do is I'll do one more register to memory move and take what's in RBX, which is, there we go, cafe, and I will put that where R11 is pointing, which is here. And so when I do one more cycle, cafe is now at address 100. And that's exactly what we wanted. So if you want to get some more insight into how these instructions are working, you can pull them up on the simulator, and that will show you exactly what's going on.